Hi there guys, well we're going to look at 9F in this video. So we'll look at an extension of matrix transformations, and the slight extension to 9E is that we're dealing with translations on top of stretches, rotations and reflections. So the book starts calling these affine transformations, and they give things in the form of Ax+b. So let's just unpack that briefly, and then let's look at example 9. So let's get me, and I've just obviously just copied this one across, and they're coming up with this kind of format here. So they're saying, let's apply a matrix transformation to a particular point, and they're calling the point X. Now that's already a little bit complicated because they're saying X is our point, and our point will be made up of the coordinate point X, Y. So they're kind of calling this some sort of vector X for our particular coordinate point, which will be, I don't know, it could be 1, 2, or whatever it is. Okay, but the X that they're using then stands for a particular coordinate point, and obviously we're going to be dealing with those in 2 dimensions. Okay, and the B which they're adding on to the end is just a translation. So they say, for example, if we want to translate a point 3, 2, you'll be getting out from applying your matrix to a point, perhaps. If you want to translate by the vector 1, minus 3, then after doing your AX, you may get out this coordinate point here potentially, and then you can just plus on your translation to that particular coordinate point or to multiple coordinate points, of course. Now, one thing to note is that the A here, so this matrix A, which we're applying to X, so we'll get some sort of matrix like this, applying to our particular coordinate point, and then we're going to be plussing on some vector transformation on the end. So a little bit like y equals mx plus c. Now, this matrix here is not necessarily a stretch, a rotation, or a single reflection. It might be a combination of those things. So bear in mind that this might already have been a combination of doing, say, for example, a rotation of 45 degrees clockwise, followed by a reflection in the x-axis, followed by a stretch in the y direction, say, for example. And so this will already be a multiplication of other matrices, which we can come up with through looking at these matrix transformations on the formula booklet. So we can take those transformations from here. So what I mean there is, like, for example, in example 7, they gave you 2 things here. In part D, they say write down the single matrix that represents a rotation of 45 degrees anti-clockwise about 0, 0, followed by the horizontal stretch of scale factor square root of 2. So the 45 degrees anti-clockwise we can take from the penultimate formula here, the one which you now see at the bottom, by replacing theta by 45 degrees in there. And then the other thing they said in part D was a horizontal stretch of scale factor square root of 2. So square root of 2, that would be the one which you now see at the top here. So we'll be replacing k with the square root of 2 in that matrix there. And then, of course, you can combine those 2 things. And the one which we want to do first needs to be on the right-hand side. Remember, this is a bit like composite functions. So if we wanted to do, say, if we want to apply matrix A to point X, remember point X being, say, XY there, then and then apply the transformation of B, so matrix B, then we would put the B on the outside. It would be a bit like doing composite functions when we're saying, look, there's f of x, and we want to do g of f of x, we put that on the outside. So you put these going from the outside, so inside to the outside there, depending on what we want to come first. Okay, so let's have a look at the question which they've got in the book. So we're looking at example 9, I believe. So example 9, there's only one example here before the exercise. So this one says, let's steal this one here. So we've got example 9 here. And it's saying the square PQRS has the following vertices and it undergoes the transformation described by this affine transformation here. Now you can see that they've come up with an image point, and the image point they're calling A dash Y dash. And the object point, so the original object, so that could be a choice of -2, 4 or -6, 3 or any one of these here. So the object point, we're not putting the dashes on. Likewise, we could call the original point P and we can call the image point P dash. And if we need to do another further transformation, we might call that P dash dash. So first of all, it says by multiplying two transformation matrices, verify that -1/2, 0, 0/2 is equivalent to an enlargement of a scale factor of 0.5 followed by a reflection in the y-axis. So this here, they're trying to say this is actually two transformations acting upon xy. So again, working from, we can actually put the xy there. So working from the inside outwards, we'd want to put on our enlargement of scale factor 0.5. So that would be 0.5 in the x direction and 0.5 in the y direction. So it would be this vector, this matrix here, followed by a reflection in the y-axis. So we put that one on the outside, so we want to do that first, and then follow it by this reflection in the y-axis. So a reflection in the y-axis would mean that any of our coordinate points, say for example we had coordinate point 3, 2, okay, perhaps not super accurately drawn on there, but there you go. If we want to have a reflection in the y-axis, that would become the point -3, 2. So we want to change all of our x values to being negative. So we will put here a -1, 0, and then a 0 and 1, because we want to keep our heights the same. Now, reflections, quick side note on this one, are given by the top formula there, a reflection in the line of y equals tan theta x. The problem that you have in reflecting in the y-axis is that the gradient is infinite. And so tan of theta will give you an infinite answer. So you have a bit of a problem in using that reflection line there. And that's a particular problem we have with reflecting about the y-axis. So the way in which you can also see a reflection in the y-axis is that it is an enlargement parallel to the x-axis with a scale factor of -1. Okay, so you could also see that as the second one there. So a reflection in the y-axis would be the same as a stretch parallel to the x-axis with a scale factor of -1. Okay, it would take you to the other side of the y-axis if all of your x numbers became negative, essentially. Okay, so there we go. So that's what we need to do. Just let's just see, have we actually answered that question yet? No, we haven't, because we need to do these two matrices multiply together. Don't need to consider this anymore because we're just interested in the matrix. We're not interested in applying it to a particular point at the moment. We're looking at combining two matrix transformations into one. So that should give you this thing here. And obviously, if you multiply that out, you can verify that quite quickly. Now, I notice in the book that actually they give you those two matrices the other way round. And in fact, in this case, it doesn't matter, but sometimes matrix multiplication does matter. You have it in the correct order. So I really think they should have had the matrix multiplication in the other way round, like I've got here. So they've got, you can see they've got the stretch coming after the reflection. So I think it's better to put it the other way around. Okay, for part B, it says determine the coordinates of the vertices of the image. Now, that's pretty straightforward because we can apply this to each of these coordinate points here. So, for example, we've got -1/2, 0, we've got 0, 1/2, and we'll apply that to, for example, the coordinate point -2, 4. Now, you can, if you want, apply this to multiple coordinate points by putting -6 and -3 there, and 1 and -7 there, and 5 and 0 there. And you could do that quite quickly on your calculator. So it might be easier for you to do this on your calculator to get your answer, which will again be 1, 2, 3, 4, 5, 6, 7, 8, 4 coordinate points there that will come out as your answer. Okay. So, but assuming you're going to just going to apply this to 1, it's pretty simple to do, of course. You do this times this, this times this, and then of course add them together, and that will give you your answer. So that's going to give you 1 on the in the x position, and then of course you do 0 times this, which is nothing, and 1/2 times the 4, and that's going to give you the coordinate point 2. Okay, so the coordinate point that's coming out of that coordinate point 1, 2. Okay, now once you've applied all of those, you can draw the original square and the image on the same set of axes. And again, you can see that one in the book. Pretty straightforward. It's a reflection, it's a rotation. And is that correct? What was it? Again, let's just have a look. It was an enlargement followed by a reflection. And then there was, oh, sorry, I forgot to add in that there was also the translation, which was actually the entire point of this exercise. So there's another translation. So translations essentially can't be combined. So there was the translation which we needed to apply to those points. Sorry, so I forgot on the bottom here that we also need that final thing here. So we need to put that on. Just put it on here as well. Plus 3, 2. It's going to give us the 4, 4. That's that particular coordinate point. Okay, so what I wanted to do as well was show you one of the questions in the book. So there's a nice investigation which is happening there, which I'm bypassing. But in 9F, we're going to look at this part B here. So for one part B, okay, so let's just do this one here. It's asking us what was the original coordinate point if we're given the image. So this is a bit like solving equations with matrices. So we've got here -4, 0, and 1, -4. And to be honest, I don't know what that set of transformations is. But that's a combination of stretches, rotations, and reflections. I don't know what that is exactly. That's acting on your coordinate point. So that's acting on a coordinate point, let's call it x, y. And then we add on 6 minus 2, and that gives us the answer -6 minus 3. Now we can kind of solve this like solving equations by taking this vector off both sides. So that's going to take you down to, of course, -6 and then -3. And let's just give myself a bit of space here. So let's give that -6 and -3, and then -6 and -2. And of course, that's pretty straightforward to do. 6 minus 6. So -6 minus 6, and then -3 minus -2 for the y direction. And so once we've taken this to the other side, we'll need to undo this. So we need the inverse matrix to apply to the answer after you've taken away that vector transformation. So for that, you can do it straight away on your calculator, although of course with a 2x2 matrix, we are told in the formula booklet how to find an inverse matrix, but you can on your calculator very quickly do that matrix to the power of -1 applied to the vector here, which is essentially a coordinate point. And that will give you your x, y. So it's just like solving equations, really. Okay, guys, well, thanks for listening in, and good luck with the exercise. It's 9F. There's 5 questions. They are good questions. These are questions which you can imagine turning up in exam situations. So get as much practice as you possibly can with these exercises.